Hi, I'm Percy with the Portland State University Department of Geology. I'm super excited to share my new modeling results for enhancing Oregon's geologic map. I'd like to start by thanking my family for putting up with my late hours of playing with data and the many folks who work in this domain that have produced such useful machine learning tools and tutorials. So the executive summary is that Oregon's geology is mapped at different scales in similar terrains. There's Sentinel-2 satellite data that are multispectral and freely available at 20-meter resolution. Using the areas that are mapped at higher resolution as training areas allows for the classification of areas that are mapped at lower resolution. Machine learning provides the algorithm for the classification, and all of this can be done with open source tools. First, let's start with the actual map, which some of you are familiar with. As you may or may not be aware, Oregon's Geologic Map Database is a unique approach to statewide maps. Most states have a map or maps at a specific scale, like 1 to 100,000. Oregon's database consists of the best available map for a particular area, so you can have stuff mapped at 24K right next to materials mapped at a scale of 1 to 250K. If you look carefully at the map, you can see places where there are actual straight lines indicating a change in mapping scale typically. Here we see the state geologic map symbolized by the scale of mapping, and it illustrates what I was just stating, with adjacent areas being mapped at greatly different scales in some places. Many of these areas with less detailed maps are, not surprisingly, in the eastern part of the state. Our department is actively involved in mapping these areas of eastern Oregon, often mapping multiple quads per field season. And I work with the mappers to supply them with elevation data and orthoimagery. In looking at the map over the last few years, I started thinking about how to use the areas that have been mapped in detail to enhance our mapping in the areas that were previously mapped in lower detail. A thesis from Cracknell in 2014 caught my attention in that he used multispectral orthoimagery and other geophysical data like magnetics and gravity to test out various machine learning algorithms in order to make an improved geologic map. He compared 5 methods: random forest, state vector machines, support vector machines, naive Bayes, k-nearest neighbors, and neural networks. The conclusion from this set of studies is that random forest is the best algorithm for classifying the geologic data they were working with. This inspired me to try training a machine learning algorithm on the higher resolution areas and use that to improve the mappings in the lower resolution areas using the random forest algorithm. The relatively recent availability of freely available multispectral Sentinel data lowered the barrier to entry. Sentinel data are available in 12 bands of various frequencies that are useful for certain specific applications. The spatial resolution ranges from 10 meters to 60 meters, but the bands most commonly used for geologic applications are bands 11 and 12. And both of these are 20-meter resolution, so that dictates the resolution of this study. Sentinel satellites orbit the Earth on a repeating pattern. In acquiring the Sentinel data for this project, I had several criteria to meet. It needs to be when there's no snow on the ground, obviously, and ideally at the low end of the vegetation growth season. So I chose late September of last year, 2021, and acquired cloud-free scenes from the USGS Earth Explorer site, one of the many sites available for getting Sentinel data. Machine learning generally falls into 2 categories: regression and classification. In regression, we are predicting a continuous variable, while in classification, we are predicting a discrete category. Since 2016, there has been an explosion of machine learning applications, and the open source community has really done a great job of putting out some amazing tools. This graphic shows most of the tools available in the Python scikit-learn library. Scikit-learn is the library I decided to use for this application. I played around with some of the random forest and support vector machine tools in ArcPro, but they didn't work very well. So I dropped down into Python to do the actual machine learning while using ArcPro for the data preparation and visualization. This could have just as easily been done in QGIS, the leading open source desktop GIS. In framing the problem, it's important to state up front what I'm trying to accomplish. Since I only have 20-meter resolution data available for this application, and I don't want to replace field mapping, just enhance it, I want to generate a map with lithologic changes that can be checked in the field. Ideally, I want a map of outcrops that we can go visit and start mapping from there. So just to be clear, I'm not trying to generate an actual geologic map. I'm just trying to generate a list of outcrops to investigate. With this in mind, I want to find a location that's close enough that I can visit it and field check my work. It also needs to be amenable to investigation with satellite data, meaning it should have as little vegetation as possible. It also should have some adjacent high-resolution mapping and some lower-resolution mapping within the same geologic terrain. With these search parameters in mind, I ended up with this location just south of Bend on the way to Burns. This is loosely part of our department's field mapping area. It's near a freeway, and it's only 4 hours away, which for mapping in eastern Oregon isn't terribly far. Geologic maps tend to be discussed in units of quadrangles, and I chose the Soldier's Gap quad as my training site, and the adjacent quad, Dickerson Flats, as the testing site for my model. So just to be clear, what I'm attempting to do here is use the spectral signatures from the earth materials in the quad on the right to classify the spectral signatures from the earth materials on the left. The spectral signatures in the quad on the right have labels assigned to them, as seen here, with 11 geologic unit classes that are present in the Soldier's Gap quad. They also show 50 random points placed in each mapped polygon in that quad. Now we are making the assumption, based on looking at the existing map and browsing the actual imagery, that the earth materials in Dickerson Flat are similar enough to those in Soldier's Gap that we can use the signatures for classification. Of course, any new areas that we try this technique on will have different spectral signatures and will need to be trained independently. With that assumption stated, we now have what would typically be a supervised classification problem. So we need to generate samples for training. To do this, I generated 50 random sample points per polygon and attributed each with all 10 bands of sentinel data. This resulted in 3,050 points, which I exported as a CSV to work with in Python. I also generated points for each raster cell in Dickerson Flat, resulting in about 1.5 million points to be classified. Random forest is an ensemble method that trains multiple decision trees on subsets of the data, overfitting intentionally, and then uses a majority vote of the individual trees to make the final classification. In modeling, we typically divide the data into a training and testing split. And scikit-learn has a nice utility for this called train test split, which is used to partition the data. In this case, I use a typical split of 70% for training and 30% for testing, which gives the accuracy results that we report. Starting with the support vector machine model, I was able to rather easily build a model and try out different parameters, resulting in an initial accuracy of 56%. And eventually, using other models like random forest, I was able to get up to 68% accuracy on the test data versus the predictions. After playing around with various parameters, I used the Dickerson spectral data to make predictions, and then took those data back into ArcPro to visualize the results. I continue to try out different hyperparameter optimizations in scikit-learn, but we may have reached the limit of what can be extracted from these 20-meter resolution data. As we see here, I've colored the map to indicate each of the classes that every point from Dickerson Flat was put into. And it looks remarkably like a geologic map of the area. The classification seems consistent with the general geology of the area, with it being predominantly dominated by the unit TB1, which is basalt and andesite, and unit TBA, basalt or andesite flow. But the lesser units are the ones we are interested in, particularly outcrops. Some checks that I've done are to zoom into an area mapped as QL, for example, and verify that the underlying ortho imagery looks consistent with the label. And every check that I've done so far makes sense. So this approach seems to be producing usable results that we can take out into the field and use to improve our mapping capabilities. We have 2 quads to be mapped this summer, and I'll be generating maps of outcrops from machine learning on these Sentinel data. While I have gotten up to 68% accuracy in further improvements to the model, it's hard to tell how much better we can do with these resolution of satellite data. One obvious improvement could be to include some topographic information, such as slope. Thanks for watching. Feel free to email me with any questions or suggestions on how to improve the method. My email is on the slide, and it's percd@pdx.edu.